SolidWorks Simulation, Lecture 16, Flow Simulation, Part 2, Mixing of Hot Water and Cold Water. And this is the model. Hot water come in from the left, and cold water come in from the right, and warm water come out from the bottom. And for the preparation step 1, we will load the software, Flow Simulation, load the toolbar, and there are 5 toolbars. For flow simulation, we only need the main toolbar. Open the project, and the procedure requires that we define the boundaries of the system. So we choose all the boundaries, and the procedure, the software will create lids to define the boundaries of the system. So now we create 3 lids or covers, so that this one will be the inlet of hot water, lid 2 will be the inlet of cold water, and lid 3 is for the outlet for the warm water. And now we go back to flow simulation, and we have finished with the first step of flow simulation, which is drawing a 3D model and create a project and define the cover or the lids to define the boundaries. And the second step, initial condition, will be implemented by the wizard. And the project name will be as default. The unit will be as default. And it is an internal flow because the water flow inside the pipe. And there will be heat conduction in this problem because we are going to define hot water and cold water. So there's no radiation, no transient effect, no gravity, for example. The gravity is not very important, so I'm not going to check gravity right now. And no rotation. And the reference axis will be in the x direction where the outlet flow is. So I always choose the outlet as the direction of reference. So it is x direction. Now for the second step, we will choose default fluid, which is the water. We'll choose water add. And then for the solid material, we choose aluminum alloy 6061. And for the walls, we can define the wall as a heat transfer wall with a conduction coefficient of 40 to 60. And the ambient temperature will be 20 degrees C or 293 degrees K. So next step, this is the atmosphere pressure and temperature at 20 degrees C and 1 atm pressure. And this velocity is for external flow, so we don't have to define any velocity here. So now, before we finish with the second step, the initial condition, let's go back to see what we did. We click next, and we check this heat conduction and then the direction of the outlet flow, and we determine that water will be the default fluid and aluminum alloy 6061 will be the default solid material, and the wall will have heat transfer coefficient of 40 watt meter square K, and the ambient temperature or the environment temperature will be 20 degrees C, and the wall will be perfectly smooth, and the initial condition will be at a pressure of 1 atmosphere pressure and 20 degrees C without any external flow. So we finish with the second step. For the third step, boundary conditions, right click the mouse in the boundary condition, insert at this surface. And this is the hot water inlet surface. So we define the inlet mass flow of 0.5 kilogram per second and define the thermodynamic parameter as 363. So it is 90 degrees C centigrade, 90 degrees centigrade, 90 plus 273. So it is the hot water inlet at a speed of volume flow rate of 0.5 kilogram per second. So this is the inlet mass flow rate. And now another inlet will be cold water inlet. I'll insert a boundary here. Also, the flow rate is 0.5 kilogram per second, but the temperature will be 20 degrees C, so it is a cold water inlet. So it is important that in defining these two inlet flows, this one is hot water, so the temperature is 363 K or 90 degrees C, and the cold water inlet will be 293 or 20 degrees C, although the flow rate are both the same, 0.5 kilogram per second. Now we're going to define the outlet. For the outlet, it is a pressure outlet. The environment pressure will be 1 atmosphere pressure and 20 degrees C. So we accept the default. Okay, we need to delete these two. Only this one will be defined as the outlet, pressure outlet. Okay, now we have finished with the third step, where we define three things. We define the inlet mass flow rate of 0.5 kilogram per second, and at the left the temperature is 90 degrees, and at the right the temperature is 20 degrees, and the outlet pressure is 1 atmosphere pressure and 20 degrees C. So this is the step 3 boundary conditions. And for step 4, we need to enter, first of all, global goal, and I need pressure, velocity, and fluid temperature, and also solid temperature. So I define the global goal as the pressure, velocity, and temperatures. So this is the global goal. But for the surface goal, I need to place surface goal on these surfaces. On these surfaces, I have defined temperature and flow rate. So I need to know the pressure and velocity for the inlet. For the outlet, I have defined the pressure, so I don't have to choose pressure. And temperature is also determined, so I only need to calculate velocity for the outlet. So now we have finished with the 4 steps, step 1 through step 4. Now we're going to calculate. This is step 5, and it will take quite a long time, several minutes to calculate. So before we stop recording, I'll let you look at the process. It is calculating, so I'll look at the iteration that is running the iteration. The system is iterating, and this is the result. I'll plot the temperature on the surface. Okay, I'll define the temperature. So this is the temperature, the hot water coming from the left and cold water coming from the right. So I may have to choose another surface or the upper surface. Okay, and I'll rotate 90 degrees. Okay, this is, no, I have to flip horizontally. So now the hot water coming from the left, cold water coming from the right, and warm water come out at the bottom. So this is how the system works, and the calculation is still working, and it is at the 90 iterations. So these few terms displayed in green are the items where the convergence has reached. So the numerical value has reached the convergence, so it's stopped. So, and other terms are still iterating. So there are still two items are still iterating, and the iteration reached about 150 iterations. So maybe I'll wait for the iteration to stop. So you can right click the mouse and maybe you can make the plot smaller. Okay, you can arrange those things using the right click of the mouse and choose properties. You can rotate the plot or magnify the plot, or setting different items, for example the velocity or the pressure distribution apply. This is the pressure distribution and this is the temperature distribution. So you can look at how the system is working. So I have to stop recording because it takes quite a lot of time. Okay, now the solution has finished. So we go to the result and we can display a cut plot for temperature. A cut plot using the XZ plot, XZ plane. And this is the cut plot. The temperature at the left is high. It is 90 degrees and 20 degrees temperature at the right. And there's a warm water at the bottom. And you can still play the animation of the cut plot. Or you can hide the plot. And we can display the flow trajectory or flow lines choosing the inlets and outlet. And we can choose arrow 3 times bigger. And we can play the animation of the flow line. And you can see that hot water coming from the left, cold water coming from the right, and it mixes at the globe. And then when it comes out, the temperature is a warm water. So this is the second part of this lecture, that hot and cold water can be mixed in a flow channel and come out as a warm water.